Good morning, all. Today we are going to discuss transistor configuration circuits, right? So far we derived the transistor currents. So far we consider only NPN transistor. In NPN transistor, collector current IC is equal to IS into e power VBE by VT, where VT is the thermal voltage. Okay, IS is the constant, VT also constant. So if VBE changes, IC also changes. If VBE constant, IC also constant. That means for a specific VBE, specific collector current. Similarly, base current IB is equal to, already you know the relation in active region. All these relation equations are in active region. IB is equal to IC by beta, or IC is equal to IB into beta. That is equal to IS by beta into e power VBE by VT. Then similarly, emitter current IA is equal to IC plus IB. Then we combine, that is equal to 1 by alpha, beta plus 1 by beta, that is equal to 1 by alpha. IC by alpha, that is equal to IS by alpha into e power VBE by VT. Now coming to the, if we consider the PNP transistor, consider the PNP transistor. Okay, almost same relations, only except the polarities are different. Here it is a VBE, here VEB, right? Okay. Now already we derived the current gains in different configurations. CB configuration current gain alpha, CE configuration current gain beta, CC configuration current gain gamma. Already we derived the current gain expressions, and also we have to express one current gain in terms of remaining two other current gains. Interrelationship between three current gains, alpha, beta, and gamma, right? Okay, for both, whether it is an NPN transistor or PNP transistor, okay, these equations are valid. IA is equal to IC plus IB, IC is equal to beta times IB, IE is equal to 1 plus beta into IB, alpha is equal to beta by 1 plus beta, beta is equal to alpha by 1 minus alpha. All these relationships are valid for both NPN transistor as well as PNP transistor. Now coming to the, okay, in last class also we discussed CE configuration VI characteristics. Now we discuss in detail about CE configuration input characteristics as well as output characteristics, right? Okay, for this is the CE configuration. Remember here CE emitter. If the emitter terminal is connected to ground, remember this one. Emitter terminal, this is the emitter terminal. This emitter terminal is directly connected to the ground. Okay. Now, what is the base? Here base is input terminal and collector is the output terminal. Now this is the input loop here. Similarly, this one is the output loop. Okay, this is the input loop and this one is the output loop. And one more thing is, in active region, what is the condition here? Input junction, that is base to emitter junction, should be forward bias. Okay, so that's why this is NPN transistor. This is the P-type material. P-type is connected to positive here. This is N. This is also N here. Now this junction is forward bias. Okay, here we have to apply the VBB such a way that this voltage makes the PN junction, that is emitter junction, emitter base junction forward bias. And similarly second one is collector base junction. Observe here, collector terminal is connected to the positive supply VCC, and here is the VBB, and the condition is VCC greater than VBB, and the condition is VCC greater than VBB, so that collector base junction is reverse bias. Okay, Suppose this is considered, this one is something like a 10 volts, this one is 5 volt, and this one is emitter terminal is 0 volt. Here 5 0, this junction is forward bias. Here 5 and 10, this junction is reverse bias. Okay. Now coming to the input characteristics. Okay, input characteristics means, observe here input characteristics. What is input current here? Input current is the IB. What is input voltage here? Input voltage to the transistor, not this voltage. Input voltage to the transistor is VBE, terminal voltage. Okay, input voltage to the transistor is nothing but terminal voltage. Here the terminal voltage is base. Here the terminal voltage is emitter. So that the input voltage to the transistor is VBE. So now the graph here, it is, observe here the graph is VBE x-axis, y-axis base current. Base current is the y-axis and base to emitter voltage is the x-axis, and different output voltage is constant. Observe here, this is the output voltage. What is output here? Output voltage to the transistor, not VCC. What is this one? This collector to emitter voltage, VCE. VCE is constant. So input characteristics are plotted. Input current versus input voltage. At the same time, we have to keep output voltage constant. Right? For different output voltages, we have to plot VBE versus IB. That describes the input characteristics. Observe here. Okay, this is the base to emitter voltage VBE. This is the input current IB, input current IB, right? And different values of output voltages. Okay. VC is equal to 0 volts. VC is equal to 1 volt. VC is equal to 2 volts. VC is equal to 3 volts, and so on. Right? This is nothing but a diode characteristics. Why? Because observe here input characteristics here. Okay, this is input characteristics. Okay, here it is a diode is connected. Forward bias diode is connected between base to emitter. Already we know that in forward bias, what is the diode VI characteristics? Nothing but like this. Okay, same thing. Okay, same thing appear here. Again, if we plot the different VC values, we get different graphs, right? Why? Because here, what is here expression is, what is IB current expression? IB current expression, IB is equal to, that is equal to IC by beta times exponential VBE by VT. VBE by VT. Okay. Okay, like this. Okay, as VBE changes here, as VBE here changes, IB also changes, right? And also, not only IB changes, if VCE changes, VBE also changes. Okay, VCE changes, VBE also changes. That's why we are getting different curves. As VCE changes, VBE changes, VBE changes, IB also changes. Okay. Okay, like that, the graph shifted towards right side. As VC increases, slowly increases. As VC increases, IB current slowly increases. Suppose this is for 4 volt. Suppose here it will be 5 volts means this is for 5 volts. That means what it indicates, as this VC increases, VBA also changes, right? Okay. That is about input characteristics. Once again, input characteristic, how to plot the input characteristics? Input characteristics is input current versus input voltage. At the same time, we have to maintain output voltage, transistor output voltage constant. For different output voltage, we are getting different curves here. Why? Because VC changes, VB also changes. Okay, now coming to the output characteristics here. Output characteristics is plotted. Output voltage, what is output voltage? Collector to emitter voltage versus output current. Output current is collector current, with the input current is constant. For different values of input current, we have to plot the output current, right? Remember this one. Okay, now here the graph look like. Already we know that for IB is equal to 40 microamperes. Suppose IB is fixed at 40 microamperes. We have to plot at the output current versus output voltage. Already we know the relation. What is the relation here? Relation is IC is equal to, observe here, IC in terms of microampere, sorry, IB in terms of microamperes, whereas IC in terms of milliamperes, right? Observe the range of base current range. Base current range is in terms of microamperes, whereas collector current range is in terms of milliamperes. Why? Because what is the relation between IC and IB? IC is equal to beta times IB. So it is multiplied with beta times IB. So that's why you are getting this type of curve here. And there is a one dotted line shown here. Below IB is equal to 0. Okay, this region is, we are not discussed so far here. This region is cutoff region. Okay, cutoff region. Already we briefly know that cutoff region is the region. In this region, both transistor junctions are in reverse bias. Both transistor junctions are in reverse bias. IB is equal to 0. In reverse bias, only reverse saturation current is flows through the transistor. That is leakage current. Okay, later on we discuss what is leakage current. Generally, leakage current flows through the diode or transistor when they are in reverse bias or when they are in cutoff region. Okay, this region is the cutoff region. Okay, in this region, both emitter junction and forward emitter junction and collector junction are in reverse bias. Now observe here, there is a one more dotted lines here in y-axis here. This region is the saturation region. Observe here, blue dotted lines, saturation region. Okay, here in saturation region, what is the condition here? Both emitter junction and collector junction both are in forward bias. Remember this one. Both are in forward bias. Okay. Okay, we will discuss forward bias in next class, right? Okay, only forward bias condition is happened. What is the VC value here? Observe here VC value. Okay, here observe here. Here VC is small. Only it will be around like this. When we plotted so and so on. Here this will become suppose around 1 volt. Okay. So when VC value is very small, 1 volt or less than 1 volt. In this case only. Okay, now we come to the, okay, now here saturation region. Now suppose I am saying, suppose this one is 2 volts, let us say. This one is 0 volt. And this one is, suppose this one is 5 volts. Okay, here I am connected some resistor here. So there is a drop across this resistor. Now this one collector voltage reduces. Suppose this collector voltage, okay, I am saying this collector voltage is 1.9 volt. 1.9 volt. Remaining is the drop across this resistor. Okay, how much drop across this resistor? Around approximately some 3 volts drop across this resistor. Now observe here, this is the one diode connected here. Okay, here also one diode. This emitter base junction already in forward bias. Now for small VC values, okay, 1.9, this diode also forward bias. So like that happens, right? When both the junctions are in forward bias, we can say that transistor is in saturation. When transistor is in saturation, maximum current flows through the circuit here. Okay, this is the case. Okay, in this case, what happened means, when VC is very small, in this region only, transistor act as a saturation region. Saturation region means both transistor are in, both emitter junction and collector junctions are in forward bias. How many are there? 61 are there. Okay. Now coming to, there is a one problem here. This problem is, okay, consider the circuit shown in figure. This is the circuit here. C configuration circuit. How we can say that C configuration circuit? Observe here, emitter terminal directly connected to the ground. Emitter terminal directly connected to the ground, and there is a collector resistance RC 500 ohm. Here there is a point X. Observe here. Okay, there is a node at that is a collector node. It will be denoted as a X, and VCC is equal to 2 volts. Okay, he given some reverse saturation current S is equal to 5 into 10 to the power of minus 17 amperes, and also VB is equal to 800 millivolts. This VB is equal to 800 millivolts. VCC is equal to 2 volts. 800 millivolts, and also beta value. Beta is the current gain in CE configuration. Now determine the transistor terminal currents and voltages and verify that the device indeed operate in active mode. Determine the maximum value of RC that permits the operation in active mode. Okay. The first thing is determine the terminal voltages and currents. Then after that, find the maximum collector resistance such that to keep the transistor in active region only. Now already we know that the in beginning we know that the collector current expression IC is equal to Is into e power VBE by VT. Okay, like that we have to calculate IC, IB and I. These are all the different currents in transistors. Already given VCC is equal to 2 volts. Now we are applying KVL to this loop here. Now this loop is what this says that VCC is equal to drop across this resistor. Current is IC current, IC into RC plus drop across collector terminal, that is X, Vx. Already we know the VCC, IC and RC. Okay. Now we can easily calculate Vx is equal to 1.424. Now observe that. Now this collector terminal voltage here it is this is 800 millivolt. This one is 0. This is 800 milli, right? So 800 milli greater than 0. So emitter base junction is forward bias. What about emitter collector junction? What is the collector voltage? Now we are calculated the collector voltage 1.424. So 1.424, not 2 volts, right? Remember, not 2 volts. Why? Because there is a resistor here. So drop across this resistor is removed, then remaining voltage is 1.424. 1.424 greater than 800 millivolts. So that collector base junction is in reverse bias. Now, observe the sentence here. Since the collector voltage is more positive than base voltage, This junction is in reverse bias and transistor operates in the active mode only. Like that, we have to verify that for the given values, we have to check. First of all, emitter base junction is forward bias. Okay, forward bias. Then check the base to collector junction or collector base junction is in reverse bias. What is base voltage? 800 milli. What is collector voltage? Already we calculated 1.4. So that this is in reverse bias. What type of transistor here? NPN transistor. Okay, that is the first part. And second part is, what is second part? Already given a RC value is equal to 500 ohms. What is the maximum RC? Such that it will maintain the transistor is in active mode. Active mode means collector base junction is okay. Here it will be 800 milli, and collector base junction is in reverse bias. That means at least worst case you can say that this is also Vx also 800 millivolts. So 800 millivolts, 800 millivolts. So that collector base junction still it is in reverse bias. So once you know the Vx and IC and VCC, now we can easily calculate RC. Okay. Now RC is equal to VCC minus Vx by RC. Now what is Vx here? Vx is equal to minimum Vx to keep the collector base junction is in reverse bias is 800 millivolts. So RC is equal to R suffix C, collector resistor, remain here. Collector resistor is equal to VCC minus Vx by IC. That is equal to RC is equal to 1041 ohms. So this is the maximum. Why? Because Vx is the minimum Vx. Okay. Okay, here it will is the 800 millivolts. Okay, that will give the minimum. If you fall below the 800 milli, then transistor enter into saturation region. Okay, up to 800 milli, okay, still it is in reverse bias only. Then the maximum, this implies that maximum allowable value of collector resistance RC. So now this one is the graph here. Okay, observe here. So this is the graph shown here. For 1.424 and the resistance is 500 ohm, 0.8 volts or 800 millivolts Vx, that is equal to 1041. Remember this one. So this is the maximum collector resistance to keep the collector base junction in reverse bias so that transistor operates in active region only. When transistor operates in active region, applications may be a amplifier. It will act as a amplifier. Okay, now coming to the another configuration, CB configuration, common base configuration. Okay, this is the NPN transistor. Here now base terminal, observe here. Base terminal is common to both input and output. Okay, this is the input loop here. This is the output loop here. This is input loop and this is the output loop. Here the common terminal is the base is the common terminal. Now what is input current here? Current flows in this direction. Remember here in NPN transistor, always current flows from collector to emitter. Conventional current. Conventional current always IA is equal to IB plus IC. Emitter current. Now we apply some KCL at this node. Outgoing emitter current is equal to sum of IC plus IB. Okay. Now here input current is emitter current is the input current. Output current is the IC is the output current. Right? Input current is emitter current. Output current is collector current. Okay. Now what are the input characteristics here? How to plot input characteristics here? input current versus input voltage. We have to maintain output voltage constant, right? Input current IE versus input voltage VEB. Now what is here? Output voltage VCB is constant. Remember here, this one is the forward bias. Whenever this one is forward bias, and also verify transistor is in active region or not. Okay, this is the NPN transistor. This one is the base terminal, and this one is the collector terminal. So base terminal connected here. This one is connected here. So now this one is in forward bias. Similarly, what about this one? Okay, this is internal is connected to the VCC positive. So that's why this one is in reverse bias. So collector base junction is reverse bias. Emitter base junction is in forward bias. Okay. Why? Because here n side connected to the negative terminal, here p side connected to the, if it is 0 or some positive. So emitter base junction is in forward bias. Collector base junction is in reverse bias. So the transistor is in active region. Okay, now input characteristics here it is. Okay, CB input characteristics. Or to plot the CB input characteristics, input voltage VBE versus input current IE when we maintain the output voltage constant. When we maintain a output voltage is constant. What is output voltage? Collected to base is the output voltage. Okay. Collected to base terminal is the output voltage. Remember here. And this one is the VCB. Collected to base terminal is the output voltage. Input voltage is emitter to base. Why? Because base is common now. Right? Okay. Now when we plot the input characteristics, almost look like a diode characteristics. Almost it look like a diode PN junction diode VI characteristics. Only one thing is, okay, already we know the relation between IC and IE. IE current is equal to IC by alpha, I think, right? IC by alpha e power. Here the what is input voltage here? Input voltage is VBE by VT. Now here this VBE changes as VCB changes. Okay, VCB changes. Observe here VCB 0 volts, VCB 5 volts, VCB 10 volts. As VCB changes, VBE also changes, right? As VBE changes, IA also changes. Okay, like that you are getting different. And compared to the CE configuration, here in CE configuration, as output voltage increases, the graph slowly input current increases slowly in CE configuration. Whereas in CB configuration here, CB configuration as output voltage increases very quickly. Okay, if it will be still, suppose here it is in 15 volts, maybe it will be look like this 15 volts. So that is the difference between CB and CE input characteristics, right? Here in CB, as output voltage increases, a graph towards like this. As CE, as output voltage increases, graph towards like this. So that is the difference. Observe here, in CE configuration, as output voltage increases, graph right side like this. Output voltage increases. Output voltage increases. Whereas in CB, this is left side. Okay, that is the relation between the VCB and VB, right? Okay. Now coming to the output characteristics. Same here, output characteristics. And observe here, this is in milliamperes, IE. This is also milliamperes. Whereas in CE configuration, IB is the microamperes range. IC is the milliamperes range. But here observe here both are in same. This is milliampere, this is also milliampere, right? And already we know that the relation between IC and IE. IC is equal to something like alpha times IE, right? Okay. Now here, sorry, this one is output current is equal to output by input. Okay, current. Output current by input current is the current gain in CB configuration. IC by IE is equal to alpha. Okay. Now, alpha, what is the maximum value alpha? Alpha maximum value is 1. So when alpha maximum value is equal to 1, what is here? IC is equal to IE. So here it is IE is equal to 0.5 milliampere, IC also 0.5 milliamperes. If IE is equal to 1, IC also 1. If IE is equal to 2.5, IC also 2.5. Right? Okay, this is an active region. Actually, the graph starts from saturation region. Okay, this is the saturation region. This dotted line indicates here below, just above the x-axis. In x-axis, this is the cutoff region here. Now here, this one is the saturation region here. Observe here, left side. Okay, that means when VCB collected to base voltage less than 0, when VCB collected to base voltage less than 0, then what happens means then only both junctions are in forward bias. Okay, here in this region also, in this region collector base junction is in forward bias, so that the transistor enter into saturation region, right? Okay, in some graphs this is not exactly, I think all are start with the same point. Okay, like this. Observe here for different values of IE, whatever may be the IE, I say also same. What is the relation is alpha times IE2, alpha times IE1. What is alpha maximum value? Alpha maximum value is equal to 1. So that's why here in CB configuration, IC is equal to or approximately equal to IE. So current gain is equal to 1 here. Current gain is equal to 1. Now this is in saturation region. Here this one is the saturation region. When it will enter into saturation region less than 0. When VCB for NPN transistor, when VCB is equal to 0.2 to 0.3 here given, then only collector base junction enter into forward bias. Now here in this case only both junctions are in forward bias, so the transistor is in saturation region. Okay, now transistor amplifying action. Okay, what is meant by amplifier? If input is like this, suppose here it is in the range of millivolts, this input is converted at the output like this. Okay, then only we can say that then only we can say that that one is in act as an amplifier. Amplifies the weak signal into large signal. Suppose this is in range of millivolt range. This is in the range of volts range. Okay, volts range means some hundreds of volts. Hundreds of depending upon the gain. So millivolts convert into 100 terms of volts in terms of voltage. Tens or hundreds of volts. So that is the amplifier action. Now observe here, given some Ri input resistance of the transistor is 20 ohms. output resistance is 100 kilo ohms. And also here output resistance R0 is 100 kilo ohms, Ri is equal to 20 ohms, and the collector resistance is equal to 5 kilo ohms. Now here calculate the input current. Input current IA is equal to input voltage by input resistance. 200 milli by 20 ohms, that is equal to 10 milliamperes. Okay, 10 milliamperes is the emitter current. What about collector current, output current? Output current, if you neglect the base or consider the alpha is equal to 1 here, alpha is equal to 1, IE is equal to IC. Now IC also 10 milliamperes. What about the load resistor here? Load resistor is 5 kilo ohm is the load resistor. So 5 kilo ohm is the output resistor. So that output voltage is equal to IL into R. So 10 milli into 5K, that is equal to 50 volts. Now coming to the what is the amplification ratio? Voltage amplification AV, voltage gain. Okay, gain, generally gain is denoted as A, suffix V means voltage gain. Output voltage by input voltage. Output voltage 50 volts, input voltage is 20 millivolts. That is equal to 250. Gain is equal to 250. So very high gain. Okay, very high gain. That means output voltage is equal to 250 multiplied into input voltage. So output voltage gain AV is equal to gain times voltage gain times gain into input voltage. Gain into VI. Okay. This is voltage gain. Current gain is 1. Remember here. IC by IE. IC by IE is equal to alpha, that is equal to 1. Current gain is equal to 1, but voltage gain is very large. Voltage gain is output voltage by input voltage, that will gives the 250 values for this case. Like that it will amplifies the low signals, low amplitude signals or very weak signals into high amplitude signals. Next, coming to the another configuration. Another configuration is common collector configuration. Here in common collector configuration, what is here? Collector node, collector terminal is common to both input and output terminals here, right? So here it is shown here, collector terminal, observe here, this collector terminal is common to both input. What is input here? Input is the collector terminal and base. Okay, this is the input here. And what about output here? Output terminal is the emitter terminal. Emitter to collector is the output. This is the emitter terminal with respect to collector terminal is the output. Similarly, base terminal with respect to collector terminal is the input, right? Now coming to the, this is simple representation of CC configuration. Okay, just what we uh, so called that terminal is common to both input and output, or that terminal is connected to ground. Here it is CB means base directly connected to ground. CE means emitter terminal directly connected to ground. CC means collector terminal directly connected to ground. But this is not practical circuit. This is what we can say a collector is common to both input and output. But in practical, okay, this is the circuit. Okay, this is not, some students are confusing. Emitter terminal is connected to ground. This is C cannot. Emitter is not connected to ground, right? Emitter connected to ground means this is the CE configuration. If emitter directly connected to ground, that is CE configuration. But here not, emitter terminal connected to the resistor and resistor is connected to the ground. So this is the ground point. Then now we can say that this one is a CC configuration circuit. Now generally a transistor are used in amplifier purpose. Okay, just it will amplify low weak signals into, okay, convert into low signals into high signals, right? Okay, for AC analysis, okay, generally transistors are used for AC signals. Okay, for AC analysis, all these DCs are short circuited, remember here. For AC signal analysis, this one is short circuit. Now this one is short circuit means with respect to AC, remember this one, with respect to AC signals, with respect to AC signals. Now observe the collector terminal here. Now collector terminal directly connected to the ground. Observe here. This is important. With respect to AC terminal, for AC signals, this we are considering the equivalent model. This is short circuit. Whenever short circuit, now this collector terminal is connected to the ground, right? Okay. Now what is output? Output is taken at emitter. Input is between base and collector. Output is between emitter and collector terminals. Remember, that's why this is common collector configuration. Common collector configuration with respect to AC signals. Coming to the biases, how to apply bias voltage is here. This base to emitter junction is forward bias, so that base, this is NPN transistor, here base is the p-type material, this one is NPN, here there is a diode, this diode is in forward bias. Okay, now coming to the reverse bias, what is here? This one is, there is another diode here, reverse bias. Now this collector terminal is connected to plus VCC greater than this VBB, so that this junction is in reverse bias. Now we can say this transistor acting as a active region. Active region, emitter base junction forward bias, collector base junction reverse bias, right? Then how we can say that transistor is in CC configuration with respect to AC. Okay, with respect to AC, all DC voltages are short circuit. With respect to AC analysis, for amplifier analysis, collector terminal directly connected to the ground, so that we can say this is the CC configuration, not CE configuration. Now coming to the input characteristics, and remember here CC input characteristics are different from remaining two characteristics. What are the remaining two characteristics? Like that exponential increase, whether it is towards like this or towards right side or towards left side. But here in this case what happened means same expression is same. Okay, expression is same, but what happened means here, this one is when VCE increases here. This is the 2 volts, this is the 4 volts. When VEC, okay, this is a, what is input characteristics? Input voltage, sorry, input current versus input voltage. What is input voltage? Base to collector voltage. Base to collector voltage. Now what is input current? IB current. What is output voltage? VEC. As VEC changes, okay, this one is changes. Now here what happens means VBC also changes. Same expression is same. What is expression? IB is equal to something like IC by beta times, and we can convert here in terms of gamma also, e power, instead of VBE here VBC by VT. Normal general expressions is VBE by VT. Now here in this one is instead of VBE, what is input voltage here? VBC. VBC by VT. So as VEC changes, VBC also changes. Like that we get the different curves, almost something like a vertical lines. Okay, that is about input characteristics. And coming to the output characteristics, so this is the CC output. characteristics. Okay. Same, what is output characteristics here? Output current. What is output current? Emitter current. Output current versus output voltage with different input current constant. Okay, this is about the graph. Okay, it is look like a similar to the same CE configuration as well as CB configuration. Only one small change here it is. Observe the range. Okay, here the IE range. Here the IE range is milliampere range. IB range is microampere range. In CC configuration, what is here gain? DC current gain. What is current gain here? Beta plus 1. Okay, beta plus 1. So that it will almost look like a CE configuration output characteristics, right? Okay, here the important observation here it is here the input currents are in the range of microamperes, whereas output currents are in the range of milliampere range. Okay, directly by observing this one graph also, there is a current amplification. Current amplification, right? And coming to the why CE configuration is preferred. Among all this configuration, CE configuration is preferred, right? Okay. The conclusion, all these things here it is simply observe here. Okay, whenever we analyze the amplifier circuit, then only we can easily understand why CE configuration is preferred, right? Why? Because for amplifier circuit, voltage amplifier circuit, whatever the requirement for voltage amplifier circuit, okay, here observe here input resistance low about 100 ohms. This is for CB. Output resistance very high, voltage gain low. CE configurations, input resistance low, output resistance high, voltage gain high. For CC configuration, voltage gain is less than 1. So for voltage amplification, if the what is voltage gain less than 1, so that not preferred. Remember this one. CC configuration is not preferred for voltage amplifications. Why? Because voltage gain is less than 1. Now here observe the voltage gain in CB configuration. CB configuration maximum is 150. What about here in CE configuration? Here in CE configuration, what is voltage gain? Voltage gain about 500. And also for voltage amplifiers, we require okay this values, right? Output resistance and input resistance values. Okay, here the mainly thing here is this one is mainly thing. Okay, high voltage gain. Okay, we will discuss this input resistance and output resistance at the amplifier stages. But coming to the here, so far why the people prefer CE configuration in voltage amplifier means voltage gain around 500. Voltage gain around 500. CC configuration is not preferred. Why? Because it is less than 1. CB configuration is not much gain. So that the people preferred in CE configuration. Okay, up to this. Okay, up to this classes, you can take this point. Okay, here the voltage gain is very, very high compared to remaining two configuration. That's why people preferred CE configuration.